for joining. So our speaker today, as I think you've all realized, is Serena Kim from Arizona, who's an expert on star and planet formation, as well as protoplanetary disk evolution. Serena did her PhD at Stony Brook, the University of New York, and then moved to Steward Observatory at the University of Arizona, first as a postdoc, and where she is now an associate astronomer. So today she'll be talking to us about protoplanetary disks in diverse star-forming environments. Serena, thank you very much for agreeing to come and speak to us, especially at, well, not too early a time, but definitely outside of normal working hours. So thank you very much, and whenever you're ready.
Thank you very much for introduction, and thank you. This is really great chance because my collaborator is right there, Tom, and I appreciate his collaboration. And I saw that Julia is there too now. So what I'm going to talk about is very observational today, and I have an expert theorist right there in your department, Tom. You can ask questions about him about a lot of theoretical questions. So if I go too fast, please let me know. Kind of slow me down. And then hopefully I will not go over time. So here I have a lot of collaborators. A lot of work was done by my former postdoc, now faculty, going to be faculty in China, Lin Fang, and Kathy Clark. I think Kathy Clark as well, because she pointed me to a certain direction when I was in sabbatical in Cambridge. She and I talked a lot about the theory and then observation, and then we started working on it, and then I met with these wonderful people, including Tom over there. And this is a part of the also work with something called Nexus, Earth in other solar system. That's an astrobiology program in US. And now we got the second round funded, which is called Alien Earth. But today I'm not going to talk about that astrobiology project. So I have some background and some things, the questions about protoplanetary disk. And then I will talk about, introduce you environments. What do I mean by those different environments? And then hopefully I'll show you some observations of disk size and mass as a function of environments. And what do we know so far, and where should we go? So it's going to be a story, a lot of storytelling. And I heard that there are some extragalactic folks in here too. So this is a location in our galaxy. That's the center of our galaxy, and we are right there in Orion arm, between Perseus arm and here's Carina. So these dots, the reason is where it's my lab, basically. This is my lab space, and I'm expanding, but I'm spending a lot on Orion right there. So I think in abstract, I wanted to actually talk about a bigger scale one at this as well, but I decided to focus on Orion this time because there was too much story to tell. In this, look at this galaxy and all these H2 regions, beautiful beads. Basically, those are where all these stars form, and so wonderful things are happening for me. So that was an M83 just now, but in our galaxy, and we can actually see more detail because obviously we are closer to them. So this is called W3 and W4, W5. So W3, W4, W5 at 2 kiloparsec at Perseus arm. It's an outside, actually, outer spiral arm. So this is where we can actually study star formation and also something called the larger scale triggered star formation. Basically, what's happening is in the OB stars in the center actually form. They basically pour a lot of UV radiation, much bigger scale than Orion I'm going to talk about. And then there's giant molecular cloud around, and then basically next generations form. So I spent a lot of time working on this too, but to have this region as a kind of example where a lot of stars form and different kind of mode of star formation may be happening in galactic scale, much smaller than galaxy scale, but to us, it's pretty large one. So now, however, I'm going to go for the smaller clusters. I show you here trapezium at the very center of Orion. So these are the typical sites of star and planet formation. And likely place for the solar system is a birthplace for us was suggested to be clusters with high mass stars around. There are good thing about using clusters, there are large sample of co-eval stars, that meaning that we can estimate age and distances. Those are very important because otherwise it is difficult to basically estimate the age. And in clusters, so there are different astrophysics that just related to us. Our topic today is ionization, and there's like a densities of flybys and encounters. But it turned out ionization plays really important role for most of the cases. So another background here is about, I'm connecting that to our solar system birthplace. It's suggested from short-lived radioactive nuclides and meteorites like aluminum-26 and iron-60, and there are many others like beryllium and tungsten. But then these are old or dying massive stars nearby basically affected us, basically when the solar system was forming in the disk. And so there are a lot of tons of people studying this. So our solar system birthplace is definitely suggested to be those clusters. So it doesn't have to be supernovae. The supernovae idea was suggested, but it could be very typically dying old star, massive star that can be affecting. So there's a supernovae or a massive star, the cold cloud, here gas and dust. Basically, it can explode. This is one idea, or UV radiation can basically heat it up and basically compress this area and basically trigger next generation of stars. And then when the stars form, the disks would be there too, and then those would be injected. So this is just one of the ideas, but it doesn't have to be supernovae. Now, another background I need to mention is this is a YSO. I'm going to use some disk folks jargon. So YSO is young stellar object, and this is a really old figure, classic figure from the Ladder and Milking and Shu and other papers. And here I show you SCDs. This is the photosphere. And then when in infrared, actually there's no photosphere for the class, something called class 0. I will use something called 0, class 1, class 2, and class 3. And what it basically tells you is basically the SCD shape and then slope. So there's something with only the envelopes when we don't see any star. And in this case, star is there, sort of, but it's very hard to observe. But infrared, we can actually see excess emission from the disk and envelope. It has some outflow going as well in the picture. And as a disk evolves, it doesn't have to be necessarily exactly the same. They don't exactly, go over use the same time. Some of them actually evolve much faster, some of them slower. So the shape of the disk, this is actually class 2 sources, and some of them are like a flat disk source too. And when it loses basically primordial disk, we call it class 3, diskless stars. But they're not exactly diskless because they could have debris disk that is generated in a second generation debris disk from the planetesimal collision. So these are the one that I'm going to use, class 0 and 1 flat spectrum, and 2 and 3. So most of the Proplyds I'm going to talk about will be class 2, almost becoming class 3 with diskless, but they are very more envelope and then disk rich. At the beginning, there is a infolding envelope, and that's basically class 0 and 1 cases. So this is kind of jargon that I would use. Another thing is that this here I show a protostar and the gaseous and dusty disk. And here, different wavelength, here's an infrared, actually basically traces different part of the disk. And this is another different kind of illustration of the disk. Here is some planet forming already and then clearing out the disk. So I will use sometimes something called transition objects. So I'm sure you might have seen some beautiful ALMA images with the rings and gaps. Those are called transition disks. From class 2 sources to actually almost class 3. Those can be observed, and then accretion, disk wind, stellar properties. We actually use optical and infrared spectroscopy to trace them. All right, so about planetary disk. And would like to mention the important time scale constraints. So that's what we care a lot about also is disk lifetime, how long would disk survive, and how the planet formation happened. So disk lifetime wise, we sometimes use something called disk fraction. I'm going to show you soon, but it seems like all the current observations actually suggest that those protoplanetary disks live about 3 to 5 million years. Normally, some of them, even in 1 million years, they are lost. But some of them even last 10 million years. That depends on initial condition and environment. So even at 1 million years, soon show the picture, 10 to 20% of disks already lost gas. So that's really fast. Maybe that's because we are tracing only the very inner part of the disk or certain size of the dust grains. So if the giant planets already formed within 1 million years, we won't be able to tell. So the mass could be locked into giant planetary small bodies. And giant planet formation from observation, we think that it has to happen very fast, within 1 million or two, because otherwise there's not enough gas or dust left for them. So here's a relevant plot for disk lifetime. So in y-axis, it shows the accreting stars. This is like IRAC, meaning that it includes up to 8 micron. And here's the age from 0 to, actually it's 100 over here, 10 million years. So and then the blue one actually shows you what each point is each cluster. And this is for the dust disk and the red dots are tracing gas, accretion disk. So it seems like accretion disk gas actually gets removed first before dust disks do. In the right-hand side, it's our preliminary work for Orion. So we have uniform sample and we derived uniformly about the disks in each clusters in Orion. And here it's called disk frequency, or it's also called disk fraction, meaning that in ONC, Orion Nebula cluster, in 1 million year, about 70-something% of them have inner disk. But already the rest of them is lost. We don't see the disk, they are diskless stars. Now that's one of the youngest one, and that NGC 1977 I'm going to talk about here later, it has about 60% disk fraction and also about 1.5 million years. So something really happened here and dispersed quickly. So they are in Orion A, similar parent cloud, but cluster right next to each other. So basically these are different clusters in Orion. Some of the Orion can be very old. So you can generally see the trend, losing disk with pretty fast. There's another observation signature. It's from Patrick Sheehan and Josh Eisner in our EOS team. So giant planets need to form very early. It is one example of gapped disks, but it's actually younger or younger than half a million year old. So these also disk mass actually suggests that you can form Jupiter already. So it should have already formed before that. So that planet formation scale is being constrained from observations. So now I'm going to talk about environment. So environment is important. And I can tell you, we see the difference. The punchline is in strong environment, disks in a way suffer maybe and disperse quickly. So do we observe that truncated disk near our star, smaller than the disks otherwise? So that's bottom line. And here I actually show you different cases though. So I categorized to extreme UV, strong, intermediate, and weak UV environment. And here is actually part of the this from the Andrew Winter's plot. And I did the same thing with what I did with Tom. So here's an extreme UV region. And then x-axis actually is increasing stellar density over here per cubic parsec. And here is the increasing UV field strength. And G naught, here we are I'm going to use something with G naught. G naught of 1 means that the radiation field around the solar neighborhood. So 1,000 times stronger for this case, 10 our solar neighborhood. And here is 10,000 and 100,000. So ONC's case between 100,000 and million, and there are even stronger cases as well. So, and then so here are a weak sort of, an intermediate, I would say, in a strong, and there's an extreme UV environment. So I'm not going to talk about this, but I will have a one slide for this extreme UV radiation. And this case, it was a Pismis 24. It was my postdoc studied about this region. In this case, we're talking about very early star, O3, not only one, there are at least 2 of them, and then O5, and then other dozens of OB stars. So this is the extreme case, very young, similar age as ONC, but it's kind of far away, so completeness can be, it's different from ONC. In this case, the disk frequency shown is only 30%, it's very low. So Proplyds, photoevaporating disks, are shown flowing away from basically ionizing sources. And in the plot that I showed you about this frequency, it appears right there, much lower than ONC in extreme cases. So that's what I'm going to tell you about the extreme case, but I'm going to spend more time telling you the story about strong cases in ONC. You have seen this picture a lot, probably. And in this case, UV field strength is about 50,000 about G0 around the O star. And I'm going to also talk about intermediate UV radiation environment. That's where Kathy said, look, it's not only O stars, B stars can damage disks too. So you got to look around it. And since I was already looking at this region, I went around and looked for it. And here we go. There were photoevaporating disks. So this case is UV radiation field strength is about 3,000 G0. And then, of course, in our really close by nearby region, they're mostly weak. So Taurus, Lupus, for instance, those are weak radiation environment. But then Tom, I don't know if you have given talk there, but he and also Cliffs, they found IM Lupi, which is in Lupus, and in like very low environment, UV radiation environment, still photoevaporating, gigantic fluffy disk. So that's there, but not going to talk about that too. So even very low UV, it plays important role. Okay, so here I borrowed Andrew Winter's plot again. Is a cluster age, basically. It's a time in million years. And here's a G0 again. Now in this case, let's start from the 3,000, like intermediate case. Even then, here's actually outer disk. So disks basically tells you that in low G0, the disk will last longer, especially those disks that we see from observations from like 70, 100 AU disks, the large disks that we see from ARM images. But those disks will go away really quickly within a million years, or even shorter time for even intermediate mass UV radiation field. So that was theoretically calculated. Photoevaporating disk-wise, so I'm going to use something called Proplyds. It's a photoevaporating protoplanetary disk. So kind of weird name. Some people really hate it, but I'm going to use that today. So this is the direct evidence of interplay between massive star and protoplanetary disk. Why is it important? Because a lot of times I showed you the cases for triggering, but it's hard to tell which star is exactly affected by this ionization. This ionizing source is right there, but there are a lot of stars. Some stars, they have a motion within cluster. Sometimes they were far away and coming in close. And how are they directly getting affected is very hard. But Proplyds gives us actually wonderful lab to study. So these Proplyds, I show you here. So the ionizing source in this case is the right-hand side. So UV light is coming this way, and there is imaginative illustration of the disk in jet source. And what we see is like this, a teardrop in a way, cometary shape, the gas bubble, and then so head and tail shape. And we also see here the shock area. So this is the basically direct evidence of interplay between ionizing massive star and the disk. Until recently, most of the cases we see these in the interaction was around O-stars, like Pismis 24, and there are ONC, especially from HST images, was beautiful and could be seen so easily. But then we found it in intermediate mass and intermediate UV radiation field as well. So today, I will show you more about the Orion. I'm sure you know really well about Orion, this beautiful belt star. This is also my lab. I spend so much time in Orion. And these are about 400 parsec away. Near Gaia distance is about between 330 to 450. But in here, ONC is about 380 to 400 parsec away. So what I'm going to show you a lot today was ONC right here, and NGC 1977, which is sitting on top of ONC, about the same age, similar age. And this is called L1641. And there is actually right here, NGC 2024, which Tom's leading a paper recently. It's much younger region. So this is Orion A cloud, and here's Orion B cloud. The Orion B cloud is younger in a way than Orion A even, but Orion A is about a million or two. Belt of Orion is a bit older. So it provides really the diverse environment. This is like a laying down region to show L1641 region. Here's ONC, that's a strong, and NGC 1977 is intermediate, and this area L1641 provides kind of weak environment. So for this, we have obtained a lot of observations. So for each dot, all these, we have spectroscopy, and we have a SED, and also color information. And in this case now, they have kinematics information too, because Orion turned out very complex. It's not exactly on the same distance. So we studied here's the radial velocity, and and then we use all the kinematics and then spectroscopic information to derive ages. So we have uniformly driven age for Orion. That's what my point is. And ONC, NGC 977 or L1641 is within a million or two age range. And I also wanted to show you how complex that region is. This is from apogee 2 plus Gaia. So it's a 6-dimensional kinematic structure. Here are 3 belt, Sigma Ori, and here is a 1977 ONC, and this is the area that L1641. So the green one is Orion A. I'm going to tell you about more. And here you can see there's the radial velocity space and parallax space is beautifully. Some of them are like slightly foreground. They are already in Orion, but they should not be counted altogether. This and this obviously is a different group. So when we measure disk fraction or cluster property, we need to distinguish that. But now Gaia is helping us to do it. So otherwise, when we had disk fraction in this area, it was heavily contaminated by this older, slightly foreground population. So when you hear about that from other clusters, have that in mind. Some of them may be contamination, but now we have a beautiful data from Gaia we can actually use to have membership. So we've done some homework, a lot of, and here was some more kinematics. Lambda Ori is not one thing that I'm going to talk about today. And I'm going back to Orion for 3 different reasons. Okay, so here are the reasons that I'm going back to. So strong UV, again, these are the tiers. You actually see a dark disk around the bright source. That's a silhouette disk, basically bright background. You can see the really bright background. So the dust actually shows up because background is really bright. And you can see that these are the trapezium stars. And you can actually see beautiful photoevaporating disk. Those stellar density here is like 1,000 to 10,000 per cubic parsec. And main ionizing sources, Theron C over here is 6.5. So Bottom line, disk in Orion Nebula cluster near massive stars is small, 20 to 30 AU, not those 120, 200 AU disks in Taurus. And here is a picture of my postdoc who did wonderful work. And here's the location of Thera-1 Ori C, because I'm going to talk to you about this. This is a major ionizing source there. And you can see that Proplyd evaporating away from that star. Here, so what we have a lot of disk sources in the cluster. So which ones then Proplyd, what is the fraction of those Proplyds among the disk? And this is the plot. So here's a projected distance from Thera-1 Ori C. And here is a disk fraction among the disk population. So if 100% of them, all Proplyds, it will be 100. But this is really right next to Thera-1 Ori C, which is all 6 star. Here we can see that it starts from about 70% and goes down. So after about 0.1 parsec, so before that is EUV dominated region, and after that is FUV. Most of the places FUV dominated region, and it's actually Proplyd fraction goes down. So here is basically the result from ALMA cycle 3 observations. PI was Eisner, and this was part of the our EOS Nexus EOS project. We basically imaged 1.5 by 1.5 arc minute within the heart of Orion Nebula. So we had optical with not only infrared spectroscopy done already so that we could have stellar property. And then we had observations of ALMA, and we discovered more than 100 disks, and over 60 of them were Proplyds. And here is the size, the radius of the disk within the center of ONC distribution is histogram. Most of them were 10. 10 is the limit for their detection, is a resolution basically. So most of them were smaller than 30, most of them were 20 AU. So it's very small. There are very few that is large. So these disks are small. Expected, right? But we are actually seeing that expected result. And for the Proplyds, okay, the Proplyds, this evaporating disk must have enough gas and enough dust. So yes, some of them do, but not comparable to those massive class 1 sources in a very quiet region. And here is something called HR diagram, temperature, effective temperature in x-axis, and luminosity in log. And these are only for the core of trapezium. So they are not contaminated. And we have spectroscopy for individual sources. So we corrected for accretion veiling, corrected for extinction, and we are plotting here effective temperature and luminosity. And we see a lot of spread within tiny 1 by 1 arc minute region. Why is that so interestingly spread out? Is there already age difference? But it turned out there are a lot of things going on to this. So here I show you some Proplyds, photoevaporating. These are all photoevaporating disks. And some of them actually don't even show much excess in infrared. So it's almost losing disk. And some of them losing little more excess than this in this case. And some of them have a huge excess. So all these photoevaporating disk has very different problems. Okay, so, and they are all over. I can show you same very young age. Median age is about 1 million years. But these sources are also very young. They are the heavily disks right next to Orion, and they're Proplyds. So these are photoevaporating, and it looks very young. But here is photoevaporating as well, but looks pretty old down here, and there are even dust disk over here that is consistent with being young age. But there are some ages, some of them actually look very, very old. This is like a below 0A main sequence. So it can spread out because of disk orientation in other regions. In strong UV environment, it's so strong that it's evaporating materials near the star so much that there are a lot of brown dwarfs. And in this case, it's a free-floating planet. So it's photoevaporating disk, and the central source mass is at most 10 to 13 Jupiter mass. It's below that. And now I'm going to show you an example, right? Not the theta on ONC, but ONC also has a B star. And there is a Proplyd that's right next to the B star. Like if it's really the same multiple system with a B star, then we expect that at least that case B star would be playing more important role. It does play a role for the disk evaporation, but it's still that O6 star far away plays more important role. So now take a look at this picture right here. This is the HST image. This is a theta on OEC or 6. You can see the photoevaporating disks right there, or the Proplyds. And here is a B star. It's a multiple system. And right next to it is a microjet photoevaporating Proplyds. So we turned out we had a Magellan AO system in Chile, and had an AO observations. Its resolution, look at this, it's about 0.1 arc second. You can already resolve this binary. And you actually have see this tail, faint fudge tail actually get bent like that. And it's right really next to O star, a B star, but it's mostly affected by O star that is further away. Okay, and another AO imaging result actually shows that they do have some kind of activity, maybe accretion, we don't know what, but there were some alpha emissions showing up and disappearing. So there are some variability in these sources as well. And I showed you this one briefly at the beginning. It's a ONC Proplyd, new data, brand new. So my PI, Nick Ballerin, used to be our team member in U of A, now in Virginia. He's taking a look at this. Fantastic data. So we asked for, after we got all this band 3 data, we asked for band 7. And no, actually, this is the band 3 data, 3 millimeter data. And then the resolution was about 24 AU at this distance. And here's the 4 examples of Proplyds for evaporating. And in here, we can actually image the dust disk pretty clean. Okay. And these are all very small. Disk size is about between 13, in this case, that's about 34, the big ones. So the dust disks are very small too. Here's one example. And these are mostly free, was from previous VLA observations. You can basically notice that these are free imaging, but in the center, that is basically the emission from the dust. Same thing here. Here's a shock area. And here's the disk. So this is new data on paper will come out, so please stay tuned. And I think I already showed this one before about the near stars, so I'll skip that. And then I'm going to now the lowest UV radiation field that we actually observed those photoevaporating dust. It was thought that only O-stars would do such damage, and then we can see those photoevaporating Proplyds. But that's not the case. In immediate case, it happens too. So it's 1977, right above the ONC. Far UV strength is about 3,000 G0, or about the distance to Proplyds we found. And here's the Running Man Nebula. It's also called Running Man Nebula. I don't know if it looked like the Running Man. And that is the earliest one, is B1. There are some other late or mid B stars. So only around this star we could find Proplyds. Okay, so here is another, it's the same plot. And this in 1970 is right below right here, slightly older, 1.5 about. And stellar density is low, about 100, not 1,000 to 10,000 like ONC. So the density is different too. And this correction is preliminary. It's about 60%. Here is a picture. So Kathy Clark asked me to go look for it. I was there doing stellar properties, and then yes, they are there in HST. So we found an archive. It was really fun. So you see that the arrow actually show B stars right there, and it's blowing away. In this case, blowing away this way. And then some of them we actually find the disks. These are the disk inside. And here's pretty faint, but these are all Proplyds. And they're very interesting jet sources as well that John Barley found. And they are about 0.03 to 0.3 parsec away. And disk sizes in this case are like a 40 to 70 AU, but they are an emission. And we don't have the dust property yet. We have a VLT time, but we need to get RMAT time for these. These central sources, I have a deep photometry done, and then we think these are also planetary mass. Should be lower than 13 Jupiter mass. So photoevaporating disk can form free-floating planets. Excuse me. And here's a B star. And these are where we found all these photoevaporating disks. What happened to this region? There is no data. So we're trying to get more HST data to find more. So only this area was covered. Here are the two candidates with the planetary mass Proplyds. I would like to mention actually here that the photoevaporation mass loss rate is about 10 to the minus 7 because solar mass per year. Accretion rate for these disks is way much lower. Accretion rates for even massive classical, T Tauri star is like 10 to the minus 9, 10 to the minus 8, 10 to the minus 10. In this case, it's 10 to the minus 7 or even higher. So in this kind of environment, even 3000 G0 case, photoevaporation wins, basically, even accretion. So it can affect very inner disk. And Tom is working on this. We just submitted the paper and working on referee report. It's in NGC 2024. It's another Orion. Also, Tom found it like, look, there is a beautiful Proplyd, and we are working on it. So this is very, very young, even probably younger than ONC, but it seems like there are two different populations near O star and B star. So that's the work ongoing. And here's some image of a alpha image, and we have a Paschen alpha and a alpha image. And here is the IRS1 and evaporating this way, and can see there's some possible jet this way as well. And we have about 8 Proplyds. So stay tuned for the result, and you can bother Tom Howard for this. It's fantastic result, actually. We found beautiful Proplyds around this region. It's in between 1977 and ONC. And we have a disk mass measurement, and in very, very young age. So some of the disks are kind of large, like I think for this one is a bit larger. And here is a projected distance from the ionizing sources. There are 2 sources for this, for each case. So we need to stay tuned for those results for that when we accept it. Okay, so in weak case, I think I'm going to skip some of the results here. But here is basically a 1641, and I wanted to actually show you about accretion. Okay, this is a HR diagram again. So we know the properties of the stars. We know the mass of the estimate of the mass and age. And accretion rate, we studied heavily on accretion rate here and variability. About 80% for classical T Tauri stars, and there are 40 to 45% of those transition disks with gaps and holes in the disk. We found a pretty good fraction of accretion disk. So that's this is the basically ONC is here, and this 97 is above. And here is the very, in a way, weak, because they do have some mid B stars, but not like a B0 or B1. The red ones are the places of transition disk potentially forming planets all over. So there are different groups actually here. So we study the accretion. How do we study accretion? In one way of H alpha, and we also are doing infrared studies. There are various line diagnostic. One known one is H alpha. And we wanted to have resolved H alpha diagnostic because there are other contaminations we need to figure out. So showing some simple examples, some of the accretion, this obviously has M star have a disk. And these are the H alpha line profiles just varying in different time. Some of the stars with accretion show no accretion later. Accretion rate is very low, actually, 10 to the minus 10 to 10 to the minus 11. And remember that photoevaporation rate for 3,000 cases, it's about even 10 to the minus 7. So it's evaporating this a lot faster, and this is accretion rate wise. There's another accretion showing, I mean, once you have low accretion, we can expect that the disk is losing material. So I didn't expect that we will see also high accretion or happening again. This is cases from low accretion and having high accretion later. And that variability can be even up to order of magnitude in accretion rate. So there are very different kind of variability, and we need to understand accretion really well. Okay, so here is complex kind of. Just take a look at here is in the similar to the accretion rate over here, and these red dots are the disks with the gaps, and they vary a lot. Similarly with all the full disk cases. So the variability needs to be taken account, and up to 0.5 to 1 dex, basically accretion can change. Now we know accretion now changes, and for these disk cases, most of the time the accretion rate is 10 to the minus down to 10 to the minus 11 solar mass per year, while the photoevaporation mass loss rate is about 10 to the minus 7 solar mass per year. So when we observe protoplanetary disk, I've talked about ion imaging in this area where giant planet and ice planets form. And as I mentioned, we are going for the IR spectroscopy as well, and for very inner part of the disk. And actually, we're going with we are hoping to get UV mission called Hyperion done so that we can study very, very, very inner disk, molecular hydrogen. Here, you might have seen these disks in nearby quiet region. They're huge, typically larger than 100 and 200 AU, but that is not the case for Orion's disks. I've already shown you they are smaller. Not 100, 200 is 20 AU, okay? And here is a comparison to from Eisner paper in our result. So here's like Ophiuchus, here's Taurus and Lupus. And you can see the Orion's case is a disk size over here, you got 10 and 100, and here's a probability. So here is the Orion's case, and Chameleon is down here too, and it's kind of older than Orion. And here's upper scale, that's also very old, much older than Orion. So Orion is smaller than the quiet region ones. We don't have this data for NGC 1977. We hope to have that one soon. And here is a distance from Theta Honori C, and there's a measurement of disk radius. And there's a trend, although there's a lot of scatter, there's a trend that's closer to the O6 star, disk is smaller. So we talked about dust disk. Gas is detected too. As a graduate student in our department, and we have 23 ARMA detections of gas. CO, 3-2, and HCO+. So using the 23, it's especially all spectrally resolved as well, and we also see the correlation. So this is actually beam size over here, so they are resolved. It's in Boyden and Eisner paper 2020. And here I'll show you the gas dust size this comparison. And here the gray one is from the gas, and this is the dust. The gas has a steeper trend. This is a distance from that O6 star again, and here's the gas disk size, closer to about 0.08 parsec, really close, right? The gas disks are smaller, so they evaporate a lot faster. And then later, it gets similar, basically. So far what we know, this is like from Stu Weidenschilling for the minimum mass solar nebula. We compare that to the mass of the disks. There are caveats of a mass disk because from our millimeter and submillimeter observations to dust, there are some assumptions going in, especially with opacity and so on. So far, minimum mass solar nebula is larger than the disk we observed. Maybe we were weird. So I just wanted to show you that, opacity matters, and we assumed optically thin disk and dust temperature. So these assumptions got into this estimate the mass of the disk. I think I'm close to the end of the talk, but I wanted to show you one recent work by Venters Visca et al. 2020, showing NGC 2024 case. One side had O star, the other O9, and the other side had B star. And here is the mass of the disk, and comparing to earlier type disks in different regions. And here is a one side of the NGC 2024, same cluster, but they were affected by different ionizing source, B and O and B binary case. So we can, here is all the sigma Orion trapezium, the ONC is right there. And for NGC 2024 in one west part seems to be very low in this case. So comparison work is going on, and I wanted to basically here show, I will actually pass those. In older regions, we found in older regions, definitely the mass and size is so smaller, but in younger ones, depending on the environment, you actually see the differences. Okay, actually, I probably want to show one mass result about here. So the dust disk mass for very early, I mentioned about class 0 and 1 and flat early, younger in a way, earlier phase disk evolution is much larger than class 2 by factor of 4, mass-wise. But the size is different, actually. Size could be very similar in a way. In class 2, get larger. Now I'm going to ask question, why do we have all these Proplyds found in Orion only? Some people ask, is Orion special? And my answer is no, because we actually paid a lot of observing time, and most of the wavelength telescopes looked at Orion deep. That's how we could find all these. When I try to look for in other regions, and Tom's trying to do that too, it was hard to do that because sensitivity just wasn't there. So there is a thing, is Orion special, or are we observing in only special case? I think it is not. And Tom probably, I don't know, I think you agree with me that these should be common. We're just not observing that much in other places. So there's a question about Proplyd lifetime, and Andrew Winter had a paper about it. The accretion rate is 10 to the minus 8, 10 to the minus 10 solar mass per year, and photoevaporation mass loss rate is 10 to 100 times larger. But how can we still see that in a 2 million year disk? In that case, their explanation is that because within the cluster they move around, those disks a little bit further away probably got closer to it. And we may not be seeing some Proplyds if they are projected in this way, line of sight, then we may be missing them too. So there's an implication for planet formation. Mass loss due to photoevaporation will definitely affect it. Giant planet formation especially, and maybe even terrestrial planet formation, maybe. So there are papers and theorists working on this. So we have a huge implication, and there's also a timeline that how fast those giant planets should form. So I think I will stop here and take more questions. Thank you.
Serena, thank you very much. It was an excellent talk. A lot of exciting results and kind of interesting science. I imagine there'll be quite a few questions. Who would like to kick off first? Okay, then I will go first. I have kind of a few questions. So you're talking about the sort of in the Orion sort of star forming region, the different sort of components of it having different ages, and this following kind of an exponentially decreasing trend in terms of the disk fractions. And I guess the ages of the kind of different sort of clusters, was that done with kind of estimated just via sort of like stellar ages? Sort of color magnitude diagrams, or? I
mean, we had basically color magnitude diagram, but also we had a spectra for all these sources. So we had we had templates from using actually Carlo Manara's templates, but we collected all these class 3 sources, diskless stars, as a pre-main sequence template. And then for higher mass stars, we have models too. So we knew the spectral type, and then of course we can calculate the so there's one thing that I didn't mention. When we calculate effective temperature, if you change the disk stellar radius, it will change.
Yeah.
I didn't, yeah, exactly. So when we go here, for these sources, I don't know if you might have noticed, and for late M stars, there were excess of late M stars that look really young. But it can be fit with a 1 million year if we use magnetic isochrones with a 10% larger disk. So some of them are magnetically active, M stars especially. If we actually put that in, calculate that and disk differently, using 10% inflated disk radius, then you can actually see that. So there are, yeah, uncertainties in this. I mean, the stellar radius.
Cool. Yeah, because I think so one thing on that, I think sort of Isabel Baraf tried some years ago to kind of explain this kind of age or luminosity spread by kind of different accretion levels very early on in the stage.
Yes.
And how successful that's kind of taken up within the community.
So our paper will be out. So Fang and me, Min Fang, led the paper. I think it will be accepted soon, very soon. And we talk about exactly that accretion, how much it will affect. So accretion will also play a role in that luminosity spread. There are a lot of things that can actually cause a luminosity spread.
Cool. Okay, so I got sidetracked. So the question I wanted to ask is, there's this sort of trend of kind of relative ages. At the moment, the way we, as you kind of said, the way we try to do ages is via just sort of stellar models, but these are still sensitive to the initial conditions at these young ages.
Yes.
So I'm wondering, in the future, would this be a kind of an additional complementary way to sort of test and constrain our age estimates of young star forming regions, at least in a kind of relative sense? Kind of
so when we do the relative thing, we need to make sure that the comparison mass range of the stars is the same. Yeah. And they were derived the same way, then definitely we can do the relative case. So Orion was good because initial condition, we expected it would be similar. And then we derived using the same model, basically. So if it's shifted, it will be shifted in a similar manner. Yeah. Systematically. Yeah.
Cool.
So this could be shifted if I use magnetic model to the right, to the older age.
Yeah, it usually goes away.
Yeah.
Okay. Tom, Rich, I'm not sure who was first.
Richard can go.
Thank you, Tom. Thank you for a very interesting talk, by the way. Really enjoyed it enormously.
Thank you.
Learned a lot from that. I'm kind of curious, of course, if we look at the exoplanet population, something in the region of about 50% of stars in the night sky seem to host a planetary system. And you made a comment during your talk that, of course, most stars form within fairly dense clustered environments and then disperse into the field later on. So given your results about the importance of ultraviolet radiation fields on the lifetimes of planet forming disks, I wonder, do you think it's easy to reconcile the observations about exoplanets and their frequencies with the typical planet forming environment that you think is somehow characteristic of an average star which is going to host a planet later on? Can we reconcile the two pictures here of planets forming in dense environments that have been quite common?
I hope we could. I think Andrew Winter has a paper. Tom's part of your author, right, for the Nature paper, trying to actually okay. There's a study there trying to explain the current planetary architecture with the photoevaporation, which actually is quite promising, I think, to actually explain that. For photoevaporation actually impacting the inner disk as well, and but when the gas is removed, how the giant planet formation, even migration would happen. So there are actually theories that I don't pretend to say that there is agreement, but I think there is a good sign that there could be agreement.
does that mean that I could could paraphrase the answer to say that the typical disk lifetime is a couple of million years if you take account of external photoevaporation? Is that essentially what's being said? That your typical star?
Typical lifetime is 3 to 5 million years, but in the one that I showed you here, so typical case actually is 1977. There's more common because it's around B stars, and in our galaxy there are more B stars in clusters. So they're more typical in a way. And in 1 million year, it's about 60% of them lost mass, but we don't know the disk mass yet. We will, compared to ONC, which is really small. The giant planet should have already formed. So if giant planet can already formed and terrestrial planets are forming, then that's actually a very good sign. We can do that if we could detect that more.
I see. So if I'm reading your diagram correctly, ONC is about 1 million years old and has something in the region of 90% of its stars have disks.
So ONC is about 1 million year. Oops.
Yep.
Okay, I have to do that. ONC is about 1 million year, and then about 30% of them lost disk already in inner disk.
Oh yeah, 30%, not 90%. Yeah, I see. Okay, great. That answers my question. Thank you very much.
Yes. Thank you.
Yeah, so first of all, I'll just say maybe a little bit more on that theme. I do have a question as well, though. So I think there's growing evidence that planets form early. We're seeing all these very young disks with substructure, whether or not there really is evidence of planet formation. And so I don't think it's necessarily at odds. I think the environmental stuff is just pushing us more and more towards that kind of picture that you have to make the planets pretty early on. And just to make it even worse, there's a point that we're sort of missing, that a lot of the planets that we're looking at are billions of years old. And if you look at, for our cosmologist friends in the audience, most stars were forming at about a redshift of 2, and the cluster environments were even denser than typical now. So, you know, the stuff we're seeing here, it was even worse possibly when the planets were being formed. So I think
that's true.
The growing thing is that planets probably just have to form really early. Whether or not the environment actually affects the planets, I don't know yet, beyond just removing the mass reservoir. But I think all the action to get the planets in there has to happen fast. And then, yeah, sure, maybe they can accrete more if the disk survives for a long time. But yeah. And then my actual question was, so we're actually on the right slide. So there's this nice plot of the inner disk frequency as a function of age, and it's fantastic to have it all for all across Orion. Do we have, is it going to be possible to get a similar sort of relation for different sorts of, like, you know, Taurus, Lupus, very low UV environments? And would that e to the minus t over 5 change?
We actually have that. We didn't plot this one. I was only showing the Orion. Min has worked on Taurus, but we don't have a Lupus, but Taurus we do. And we can basically, what we do is that we get that spectra from them and then reprocess them in a uniform way. So that's how we can compare them. A lot of people just take literature here and there, but they're not the same mass. They're not the same in a way. So Taurus, we do have it. We could add it. And NGC 2024, we're studying that too, but we don't have the plot yet.
Yeah. And just, I don't want to keep everyone any longer really, but one thing that could be interesting is, as we've sort of already said, this is just an inner disk lifetime, inner disk frequency, but you actually destroy potentially a very large fraction of the disk really quickly. So although, 70% of the disks in the ONC, 70% of the stars have disks, they're really small. So I wonder if there's another time scale that could be plotted like this, something as a function of age, but to do with the fraction of disks that are, I don't know, undersized or something compared to your average, or your low mass star forming region. But maybe that's something.
I think we should try that for our next paper, probably, Tom.
Just a thought at this stage.
Yes, I mean, in this case, it's inner disk, but it includes IRAC data as well. Yes, Richard?
I might ask just a follow-up question in that case, because this plot raises as many questions as it answers, I think, if you don't mind me saying so. So what we're looking at here is quite a diverse set of ultraviolet radiation fields for each of these different subclusters within Orion. Is that right?
Yes, correct.
It's very strange to my mind that you can fit a single function to all of those points, given the very broad spread in the ultraviolet radiation fields, which are being experienced in each of those different environments. That almost suggests that ultraviolet radiation fields don't affect the lifetimes of disks, doesn't it? Given that you've got a universal function that fits everything so beautifully. I mean, it's not often that you see a set
of so
like that. Mm-hmm.
So most of these stars region have all stars. So
okay.
Except NGC L641,
yeah,
everything else has all star in
so
that.
It's quite
field.
uniform.
Yeah. So
what would be a really nice project would be to do that for other clusters which don't have O stars, and see whether that e to the minus t divided by whatever you need to have has the same exponential form, but perhaps a different e folding time.
Mm-hmm.
And we might predict a longer
we need some more uniform data, right?
Yeah, it would be interesting to try to do that. So divide clusters according to averaged multiple of G naught, and then see whether or not UV radiation fields really do affect the existence or otherwise of disks, or at least their lifetimes that you derive from that nice exponential decay.
Mm-hmm. That's very correct. And this it's a very, very extreme UV case. We actually see very low disk fraction, but in this case, compared to when C was the more extreme UV, but of course then the sensitivity was different, so we need to correct for that too. Okay. So the question remains, that's a very good question to answer.
Thank you, cheers. Thank you.
Yeah.
Does anyone have any final questions for Serena? Okay, in which case then I suggest we thank Serena again. So Serena, thank you very much. It was a really interesting talk and a great discussion afterwards. Round of applause are always very tough, but I'll kind of lead it on behalf of everyone. So I think we will kind of stick around for some sort of informal